Okay, we're going to finish the chapter on transistor bias circuits today to discuss a very important section called troubleshooting. You are, as technicians or engineers, you'll have to be able to work practically one day in the field, and you'll have to be able to do troubleshooting, especially also on biasing circuits. There may be something that's burned out or opens or whatever, and you should recognize what the reading should be. Knowing that you've got the theory now, you also have to be able to do some practical work on these circuits as well. So let's just have a look at the textbook. I've marked the introductory paragraph there. 5.4 troubleshooting. In a biased transistor circuit, the transistor can fail, or a resistor in the bias circuit can fail. We will examine several possibilities in this section using the voltage divider bias arrangement. As we know, most popular, most stable of the bias circuits that we have discussed. Many circuit failures result from open resistors, internally open transistor leads and junctions, or shorted junctions. Often these failures can produce an apparent cutoff or saturation condition when voltage is measured at the collector. So you can already see that it is important that you know what are the conditions for saturation and cutoff might be, or should be. Right, then on the next page, troubleshooting voltage divider bias transistor. If we go and look at the transistor circuit there, of course, if I have a circuit, as you will also build in the laboratory, you will have to do your calculations on based on the resistor values, voltages that you were given, and so forth, to determine the terminal voltages at least. Terminal voltages we know as being VC, VB, and VE. All right, now as soon as you've calculated these values and you go and measure these values on the circuit that you've built or the circuit that you want to do troubleshooting on, but say for instance you built this biasing circuit like here in figure 525, and say for instance it works. How do I know it works? I have to go and measure the voltage and compare them with my calculated values. And how are they going to compare to my calculated values? Are they going to be exactly the same? Of course they won't be exactly the same. They will be in the vicinity because we make some assumptions. We assume that forward biased base emitter junction is 0.7 volts, which of course could be much less or even more. All right. Resistor values we take as precision resistors. We take a value of R1 as 10 kilo ohm, for instance. Most probably 10% tolerance resistances will be used. So you can see that I make some assumptions in my calculations that of course will not be true when I do it practically, to go and measure these voltages. But anyway, let's have a look at the faults discussed in this section of the book. The ones that discussed here in your book will give you a fairly good foundation. I say for this type of bias circuit, a particular group of faults will cause the transistor collector to be at VCC when measured with respect to ground. What do I know if I go and measure the voltage VC or VCE and it's equal to the supply voltage VCC? Then I can see the transistor is in cutoff. Now then I must go and find out what is the problem. Why is it in cutoff? Alright, 5 faults are indicated in the circuit in figure 526A. The collector voltage is equal to 10 volts with respect to ground for each of the faults, as indicated in table part B. In the table part B. Also for each of these faults, the base voltage and the emitter voltage with respect to ground are given. So if you go and look at that table, I can see there that they say fault number 1, the description for that is that R1 is open, voltages being measured, VC is 10 volts, VE 0 volts, VB also equal to 0 volts. And if you go and look at the explanation on page 237, just below figure 526. Fault 1, resistor R1 open. Resistor R1 is what? Part of my voltage divider bias. Now, so say for instance R1 is open. R1 is open. What's going to happen in the circuit? That's why I said you must understand how the circuit works. Remember I said if I want to use the circuit for linear amplification, I need to bias it first. In this case, as we've seen, most stable voltage divider biasing will give me the most stable Q point to do my amplification from. But if R1 is open, no voltage going to reach my VB. My VB is going to determine my biasing current IBQ. So if there's no voltage there, what's going to happen? IC, would I know? IC is equal to what? Beta DC times IB. So IC is going to be 0. So what am I going to measure at VC? This transistor is going to act like what? If IB is 0, IC is equal to 0, acts like an open switch. What am I going to measure between the collector and the emitter? Supply voltage, as we've seen in the table there. Ne? Supply voltage, so I can see that the transistor is acting like an open switch. So it could mean that the transistor was biased into saturation, but I want to use it for linear amplification. So the design that I've done wasn't designed that way, so there must have been something wrong. So most probably R1 is open. So let's see what they say further there in the textbook. This fault removes the bias voltage from the base, thus connecting the base to ground through R2 and forcing the transistor into cutoff because VB is equal to 0, IB is equal to 0. The transistor is non-conducting, so there is no IC and therefore no voltage drop across RC. This makes the collector voltage equal to VCC, acts like an open switch. Since there is no base current or collector current, there is also no emitter current, and of course then VE will also be equal to 0. Alright, so that could be the mistake or the problem in that case. No voltage is reaching VB, so it acts like an open switch. Say for instance fault 2, resistor RE is open. What's going to happen if resistor RE is open? Let's just clean this up. Let's say now resistor RE is open. What's going to happen? I have my supply voltage, my voltage divider works. We've previously calculated that the VB, you should have done your calculation, so I can see that my voltage divider is still going to work. I would be able to calculate VB. So VB would calculate voltage divider R2 over R1 plus R2 times VCC, and I get a value of 3,2 volts. 3,2 volts. So at VB, I should still get the value of 3,2 volts. And so if I calculate VB is equal to 3,2 volts, what is VE going to be equal to? What is VE going to be equal to? If I look in the circuit, I've calculated that and I've actually measured that. Now 3,13. So I can see there's a small difference because of the assumptions that I have made. Alright? So what is the difference between VB and VE? We assume again approximately 0,7 volts, which should give me a value of 2,5 volts. I can see I should actually then measure 2,43. But remember, this resistor is open. So what am I going to measure at VC? Is there going to, of course, there's going to be no voltage drop over there. What am I going to measure at VC? Remember now, because this resistor is open, RE, what's going to happen to IC and of course IE? No current's going to flow, né? If no current's going to flow, what's going to happen? What am I going to measure? Let's have a look there in the textbook. Fault number 2, resistor RE open. At the bottom of page 237. This fault prevents the base current, emitter current and collector current except for a very small ICB0 that can be neglected. Since IC is equal to 0, there is no voltage drop across RC, therefore VC again will be equal to VCC, which is 10 volt. It'll act like an open switch. So the voltage divider formula will produce that VB is still the 3,2, which actually was measured in the example there, 3,13. And when a voltmeter is connected to the emitter, it provides a current path through its high internal impedance, resulting in a forward biased base emitter junction. Therefore, the emitter voltage is VE. VE is equal to VB minus VBE, as we've just discussed. Should be 2,5. We measure about 2,43. All right. But we know, as they said here, say here as well, VBE is 0,7. The 0,7 is assumed for purposes of illustration, but it may be much less. Okay, so you might measure something else. Let's have a look at the third fault. It says the base internally open. If I go back to the table, they give me the values there. Base internally open, VC again 10 volts, VE 0 volts, but still at the VB of 3,2 volts. So look at the fault. The fault says the base internally open, so it's inside the transistor itself. So if I go and measure on the outside, on the terminal, I'm still going to measure my VB because the track is not broken there yet. That's why I still measure my 3,2 approximately voltage that I've calculated. So an internal transistor fault is more likely to happen than an open resistor. Take note of that. Again, the transistor is non-conducting, so IC is equal to 0 amps. Base is internally open. VC is equal to VCC, 10 volts. Looks like an open switch. Just for the case as for the open RE, the voltage divider produces 3,2 volts as the external base connection. The voltage at the external emitter connection is 0 because there is no emitter current through RE and thus no voltage drop. Alright, so you have to be familiar with how the circuit works and what you expect to measure to be able to diagnose what the problem might be. Let's have a look at fault number 4, emitter internally open. Again, the transistor is non-conducting, so IC is again equal to 0 amps. And VC is equal to VCC, again 10 volts. Just for as for the case for the open RE and the internally open base, the voltage divider produces 3,2 volts at the base because the transistor is internally open at the emitter. The voltage at the external emitter lead is 0 volts because that point is open and connected to ground through RE. Notice that faults 3 and 4 produce the identical symptoms. Still the transistor that is faulty, so you'll have to replace the transistor. Let's have a look at fault number 5. Collector now internally open. Now we've looked at all 3 terminals. Now what's going to happen when the collector is internally open? Since there is internal open at the transistor collector, there is no IC again, therefore VC is going to be equal to VCC, which is 10 volts. In this situation, the voltage divider is loaded by RE through the forward biased base emitter junction, as shown in the approximation equivalent circuit. The base voltage and the emitter voltage are determined then as follows. VB, because of the loaded resistor, R2 in parallel with RE times VCC plus the 0,7 volt drop is going to give me approximately 1,1 volts. So VE is going to be 0,7 volts less than that. So be familiar with the voltages that you would be measuring approximately for these different conditions. There are 2 possible additional faults to which the transistor is conducting or appears to be conducting. based on the collector voltage measurement. The resistor RC is open. What's going to happen when the resistor RC is open? For this fault, which is illustrated in figure 528, if we go and look at figure 528, faults for which the transistor is conducting or appears to be conducting. Okay. The collector voltage may lead you to think that the transistor is in saturation, but actually it is non-conducting. Obviously, if RC is open, there can be no collector current. In this situation, the equivalent bias circuit is the same as for fault 5 as illustrated. Therefore, VB is going to be 1,11 volt as we've calculated in the previous fault, and since VB junction is forward biased. So VE is going to be 0,41 again. When a voltmeter is connected to the collector, to measure VC, a current path is provided through the internal impedance of the meter, and the base collector junction is forward biased by VB. So therefore, VC is equal to VB minus VBC. So it's again the 1,11 volt that I've measured at the base, minus the 0,7 volt, because now it's forward biased. This is in saturation, as we've seen in the previous chapter. Again, the forward drop across the terminal internal transistor junctions depend on the current. We are using 0,7 volt just for illustration. Alright, so if I go and look at this circuit, and that resistor, for instance, is open, again, there's going to be no IC. What am I going to measure? At VC, we've done the calculated values at VB. So at VC, when I'm going to measure from VC to ground, what should I measure? As I've calculated here, VB minus VBC is that 1,11 volt minus 0,7 is going to be 0,41 volts. Like indicated here, 410 millivolts on my multimeter. Alright, resistor R2 open. If resistor R2 is open, what's going to happen in that case? Let's have a look. When R2 is open, my voltage divider, remember I used the voltage divider R1 and R2 to determine VB, to give me my Q point more or less in the middle of the load line. So now the voltage divider is not going to work anymore. All the current is going to VB except the voltage drop over R1. So most probably what's going to happen is that IB is going to be much too high, and I know IC is equal to beta DC times IB. If I keep on increasing IB, IC will increase, but this formula is only true up to a certain point, which is called IC sat. So if I increase IB higher than IC sat, to cause IC to be higher than IC sat, then it doesn't matter. If I increase IB more, I cannot get more than the saturation current. But let's see what the textbook says. When R2 opens as shown in figure 528b, the base voltage and the base current increases from their normal values because the voltage divider is now formed by R1 and beta DCR in base. In this case, the base voltage is determined by the emitter voltage. VB is equal to VE plus VBE. First, verify whether the transistor is in saturation or not. Okay, so you have to do some calculations first. How do I calculate for saturation? Again, we normally assume VCE sat to be approximately 0,2 volts. So IC sat, VCC minus VCE sat divided by total resistance. In this specific circuit, it's going to be RC plus RE. I get a current of saturation current of 6,67 milliamps. Then I can calculate IB sat by using the ratio of beta, and I get a current of 22,2 microamps. Is going to give me a saturation current for this circuit of 6,67 milliamps. Now, assuming that the transistor is saturated, the maximum base current is then determined. R in at the base I can calculate. IB base is then going to be VCC divided by the total resistance R1 and R in at the base, because R2 is open. And this gives me a current of 66.2 microamps. Now, if I go and compare with IB sat of 22.2 microamps, then I can see that this is much larger. So since this amount of base current is more than enough to produce saturation, the transistor is definitely saturated. Therefore, VE, VB, and VC are as follows. VE is going to be IC sat times RE, Ohm's law. VB is going to be VE plus VBE, Kirchhoff's law. And VC is going to be VCC minus IC sat RC. So there are the voltages that I will measure in this condition. So again, I think it is clear that you know how the circuit works. Voltage divider biasing common emitter circuit, the one that you will also build in the lab, and how to do the fault finding. To be able to do the fault finding, you have to know what to expect to measure. So you'll have to do some calculations, and you'll have to apply your basic theory that you've learned on these circuits. Anyway, again, you have to read through. Make sure that you understand, do the relevant questions, and then, of course, very importantly, for test and exam purposes, the basic problems. Just make sure that, that you note here that the basic problems are now 33 to 37. And then we skip the applications part because we do our own practicals in our own laboratory. We do then again the part 42 to 46, which I think is based on the data sheet problems. So the application activity problems is skipped, and then from 40 there's some data sheet problems, just to make sure that you understand how the data sheet is used. Just take note there's an error in the circuit diagram of figure 546. Figure 546, it gives you a picture of a breadboard with a transistor circuit built on a breadboard. Of course, if you have to go and do a fault finding on that circuit, I would suggest that you redraw the circuit, you draw the schematic diagram of the circuit so that you can see, because the color codes are given of the resistors, so you can see what the resistor values are, and which resistors are then R1, R2, RC, RE, and so forth, for whatever circuit this might be. Also, just to take note, make sure that you see how this guy in this problem used this, the multimeter. Remember, I've told you we read from left to right. So if I ask you to measure VC, you put the red lead on the collector and the black lead on ground, and you will get a reading of the voltage at the collector. But I can see in this case that the guy swapped it around. The only purpose for that is he wanted to display negative values, positive values, because they should be negative. If you go and read in the question says that there's a PNP device. A PNP device, I would expect negative voltages, especially like in the example I've shown you in the previous section. So make sure when you do your calculations that you get negative values, and don't be confused by this method of measuring to get positive values. Alright, that concludes this section.